In this video, I'm going to talk about business applications of the first and second derivative. So let's say you're a small businessman. You've just started your own business in your garage making dining room tables. This graph represents the cost that you have to spend, your expenditure for producing each table. Not the amount that people are paying you, not your profit, but how much it costs you to make the tables. So notice for 0 tables it costs $300 because you have to have some tools to get started with. Okay, so that's kind of your startup cost for your business. You have to have your woodworking tools and so forth in your garage. Maybe a space heater in the wintertime or something like that. Then to make one table, it costs you about $800. So that would be the cost of your tools, but also the wood. Okay, so you had to buy some wood now to, so the wood and the tools cost you about maybe $800 to make a dining room table. So you're probably going to sell it for more than $800. Then when you go to the second table, it doesn't cost you a whole lot more than the first table because you already have the tools, you already have the garage. Now you're just maybe buying a little bit extra wood, and maybe when you're working on both tables at the same time, so you're even saving some labor costs and some time costs. So it doesn't cost you a whole lot more to make the second table as it does the first. And the same thing with the third, a little bit additional wood, but other than that, it's not costing you a whole lot more. So why would your costs go up then with the fourth table? Well, maybe at this point you are about at the limit of how much you can do in 1 week by yourself. So you have to hire your brother-in-law, Frederick, to come in, and Frederick's going to help you. He's a good woodworker. You pay him a little bit extra to get that fourth table done. And then when you get to the fifth table, you're going to have to hire him for like a half a week because it's getting to be too much. And so forth. Your costs are going up now because you have to hire extra work because you can't make all those tables by yourself. And when you get up higher here, maybe you don't fit in your garage anymore and you've got to start paying rent on a building. So all those things, labor costs, tools, materials, all factor into cost of the building. And that's why this cost curve isn't necessarily linear. It curves kind of depending on the situation with the products you're making. Now a business person would want to know how to minimize their costs. They want to minimize their costs so obviously they can maximize their profit. So we want to know what's called the marginal cost. The marginal cost is the rate of change of the cost per quantity, okay, of tables, the cost per table. So the rate of change of the cost per table here, or the instantaneous rate of change at each one of these points, is the first derivative. So this f2 of x right here, this is actually f prime of x. This is actually f1 prime of x. So here's my cost function, and this is called my marginal cost, which is the rate of change of the cost per table. So I want that to be as little as possible, obviously. I want my cost to be minimized. So how do I find those values? So we could compute marginal costs for 1, 2, 3, and 4 products. So I'm going to call this f prime, f1 prime of x. So f1 prime of 1, f1 prime of 2, f1 prime of 3, and f1 prime of 4. And I've gone ahead and computed those. I put this into my calculator. I substituted 1, 2, 3, and 4 for x, and I got these values, which will really make sense when you see them on the graph. 299, 96, 91, and 284. So what I calculated were the y values of these 4 points here. And you can see here that my costs are at a minimum when I'm making around 2 to 3 tables a week. When I start getting to 4 tables, it's not bad. But when I jump up to 5 tables, my cost per table is going up, and so my profit's going down at this point. So my profits are at a maximum and my costs are at a minimum right here. Now I won't say my profits are maximum, but my cost per table is at a minimum. So that's a good thing here. I might make more profit overall when I make a whole lot more tables, but for right now I'm operating at a very efficient level by myself here, making 2 or 3 tables per week. Now how could you find exactly when the marginal cost is at a minimum? Well, I would want to know what the minimum value of my first derivative is. So to find the minimum value of f prime of x, I would set f double prime of x equal to 0. So in other words, I want to know when the slope of my derivative function is 0, because that would be the vertex down here where I have a horizontal slope. And so I'm going to find f double prime. So I'm going to take the derivative of my derivative. So f double prime of x then would be 99 times 2x, so 198x minus 500. So setting that equal to 0, I would get 198x equals 500. X equals 500 divided by 198, or 2.525 products. Okay, in this case, dining room tables. So that's where my marginal cost is at a minimum. Another type of graph a businessman might use is a profit graph. So they keep track of their profits for 1 table, 2 tables, 3 tables, 4 tables, 5 tables. I'm not sure what they're selling these for. It looks like I'm not making much profit per table. I'd probably, it might make more sense to let's make this 100, 200. Well, of course, if I do that, I've changed my equation. But we'll just say he's only making $10 of profit on maybe $20 of profit on his first table. He'd make about $40 of profit on his second table. When he gets up to 3 tables, it looks like he's making almost $50 per table profit. I think I'd want a little more profit than that personally, but I probably should have made a different graph. But anyway, if f1 of x represents profit, where is profit maximized? Well, profit is maximized when we're at the vertex of the graph, obviously right here at the vertex. So how do I find the vertex? I set the derivative function, this is f prime of x here, the derivative function equal to 0. So where f prime of x equals 0. So I'm going to say negative 3x squared plus 2x plus 23 equals 0. I'm going to have to use the quadratic formula. Negative 2 plus or minus the square root, b squared minus 4ac all over 2a. So put all my numbers in here. 2 times negative 3. Once again, you can do this on your calculator. I did this on my calculator, and I got 2 different values for x. Okay, 3.122 and negative 2.45. 3.12 and negative 2.545. Obviously, I'm not interested in a negative number of tables, so this tells me that about 3.12 tables, I'm making my maximum profit here. So these are both examples of where a derivative is used in business for business cost functions. And if you go into business, you will be taking calculus for business, and you'll be doing problems similar to this. They aren't terribly it's not very difficult calculus, but it is calculus. Now, another example in physics. In physics, you may, if you've taken physics, you may have seen an equation that looks something like this. Distance is equal, or displacement usually it's called, is equal to let's see, something like x, or maybe you have a constant like 3 plus 5t minus 9.8 t squared, something like that, where you have some sort of a parabola that represents projectile motion. So basically this is saying it starts at 3 and it goes up, it comes down. Notice that I have the t squared is at the end. That's usually the way it's written in physics. But this would be an upside down parabola. It has a y-intercept at 3. I don't know if that number is reasonable in the middle, but it basically goes up and comes down. So don't graph this and go, oh, that doesn't look like that, because I'm sort of making up this middle term. This is the 9.8 meters per second squared, which is the acceleration due to gravity. So if I want to find the first derivative, d prime, I would get, and we would actually call this d of t and d prime of t because my input variable is time. So d prime of t would be 5 minus 2 times 9.8 would be 19.6 t. So I have some sort of a line with negative slope going, so something like this, all right, going down like this would be my, and actually I'm going to change that just slightly. I happen to know that the line would go right through here at 0 because that's where the maximum value would be, so that's where the derivative function would be 0. Up here we would have positive acceleration or positive velocity. Down here we would have negative velocity. Okay, so positive values for y or velocity and negative values for velocity, because the first graph is the position of the ball at time t. So this one tells you position at time t. This tells you the rate of change of position over time. And the rate of change of position over time is velocity. So this graph tells you the velocity at time t. So this is positive velocity, 0 velocity, negative velocity, because going downward it counts as negative velocity. Then if I did the second derivative, I would end up with just negative 19.6. Oh, you know what? I did this wrong. Sorry. This would be negative 4.9 t squared. And this would be, because it's 1/2 times the gravity, and this then would be negative 9.8 t, and then this would be negative 9.8. So my second derivative would be negative 9.8. Now the reason I wanted to put the correct numbers in here, this would have a slope of negative 9.8 because negative 9.8 meters per second squared is the acceleration due to gravity. So this is saying that as the ball is traveling, the rate of the velocity is continually decreasing by negative 9.8 meters every second because it's being dragged to the ground by gravity. And then my acceleration graph, which is the third equation here for the second derivative, is acceleration. So the acceleration at time t is the rate of change of velocity. How much is velocity changing? Well, this has a constant acceleration of negative 9.8 meters per second squared, which is just the acceleration due to gravity. Gravity pulls things down at an constant acceleration of negative 9.8 meters per second squared. So the velocity increases as something drops to the ground, but the acceleration, the rate of change of the velocity, is a constant. So these are, once again, the original function and the first and second derivative are position, velocity, and acceleration. So those are two different examples of where first and second derivatives are used.